So with permutation and combination, there are actually three things that you must know. Generally, three things that are useful. First is permutation with repetition. Second would be general permutation that does not involve repetition. And the third would be combination. So in permutation with repetition, you can actually classify is a bland case of repetition, and the second is 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 just repetition that we generally find in questions. But the first one, the bland case of repetition, is something that I like to call as the bland case of repetition. It's not a formal name. I will explain what I mean by bland case of repetition. So let's start with the bland case of repetition in permutation. So what I mean when I say bland case of repetition in permutation, I talk about questions where, for example, you have been given three samples or three choices, and let's say you have to form a three-digit number using these three choices. You have to fill in these three slots, with the available choices by selecting one of them. So what we do is that what it means is that we have to find three-digit numbers, but the condition is that the only numbers that you can use in order to form those three-digit numbers are these numbers. So for example, 132 is a viable three-digit number because it uses numbers from this set, and say 111 is a viable number because it uses numbers from this set. But say a number like 101 is not viable because 0 isn't in this set. 0 does not belong to this set. So you only have to form numbers from the set of 1, 2, 3. So how do we find out how many numbers that are possible using these three numbers? In the first slot, I can fill either 1 or 2 or 3, any of these numbers. So I have three available choices for the first slot. So there are three numbers that can be filled in the first slot, and the same with the second slot. There are three numbers that I can fill in the second slot, and there are three numbers that I can fill in the third slot as well, because of the fact that repetition is allowed. So for example, numbers like 111, where 1 is repeated three times, and like 222, where 2 is repeated three times, are allowed in this case. This is what I like to call as bland case of repetition. And in permutation, you actually multiply the number of choices that you have to find the solution, to find the total number of possible outcomes there can be. So in this case, the total three-digit numbers that can be formed using these three numbers, which is 1 to 3, is actually 3 times 3 times 3, which is 27. There are 27 three-digit numbers that can be formed using 1 to 3 as numbers, as the only numbers that are viable. So why is it that we multiply the choices? Reason for this is that let's say we take 2 to make it easier. Let's say we take 2 slots. So I have three choices and I have 2 slots. So in the first slot I can fill it in with 3, and the second slot I can fill it with 3. So let's say I fill the first slot with 1. Let's say I fill it with 1. When the choices are 1, 2, 3, and it starts with 1, the numbers that I can find would be 1, 1, and 1, 1, and 1, 2, and 1, 3, because the first number is already selected, which is 1. I can cycle through the three numbers that are available for the second slot, and that's why if I had only one choice for the first slot, let's say Let's say if I had only one choice for the first slot, then because of the fact that I can fill either 1 or 2 or 3 in the second slot, the total outcome would be 3 numbers. And so for the second choice, there are 3 possible numbers that are possible even for the second choice, and same for the third choice in the first slot, which is 3. There are 3 possible numbers that can be formed. The total numbers that can be formed is 3 here, 3 here, and 3 here, which makes it 9, because we multiply the choices that we have for every slot there is. So because of the fact that for every choice that we make in the first slot, there exists number of choices that are available for the second slot to be filled. And because this is true for every choice that can be filled in the first slot, we multiply them because we have a number of choices. That's why we multiply the choices we have for every slot there is. Okay, but in permutation with repetition, for the second case of permutation with repetition, you generally don't have repeating numbers for all three slots that can be filled. In the second case of repetition, there's actually defined or limited repetition that can be done. The second case is about limited cases of repetition. So in order to explain limited cases of repetition, let's take an example. Let's say I have the words in the let's say I have the alphabets in the word apple, and I have to find the number of rearrangements that are possible using these five numbers, these 5 alphabets. Then you can somewhat get an idea by seeing that there's only 2 things that are actually repeating, which is this P and this P. We actually, in order to solve questions with limited repetition, like this one, where the only cases of repetition are with these 2 P's, you take 5 slots. There are 5 available alphabets that you can fill in the first slot, which are A, P, P, L, and E. These are the 5 alphabets that you can fill in the first slot. But remember that because this is a case of limited repetition, you cannot repeat the alphabet that has already been filled in slot 1. So for example, a word like A, and A, this is not applicable. In the previous example, you saw that 1 was applicable because it was a bland case of repetition. But in this case, it's not allowed. In this case, if the word has already been set in the first slot, then it cannot repeat in the second slot. For the second slot, there's only 4 available choices. So for example, if I filled in A in the first slot, then for the second slot, I only have P, P, L, and E to fill in with. I only have 4 choices for the second slot because the A has already been filled in. So let's say I fill the second slot with E. Now there's only 3 choices for the third slot because the first and second slot has already been filled with one alphabet, and the 3 choices that are available for the third slot are P, P, L. Remember that P has been repeated twice, and that's why let's say I filled this one with P, and now for the fourth slot I have only P and L, and let's say I fill it with L and the last one with P, because for the last one there's only one choice. So it means that I have 3 choices for here, 2 choices for here, and only 1 choice for here. So the number of choices reduces as we go on forward because of the fact that repetition is not allowed. Because of the fact if an alphabet or a word has already been filled in with the first slot, then it's not available for the rest of the slots there are. And that's why the number of choices reduce. And like I said earlier, you multiply the number of choices that you have for every single slot. And I have already explained to you why we multiply the number of choices. So this is what you would get, what you would gotten if you were to find the if you had to find the general case of permutation. But because of the fact that there's actually two repeating alphabets, which is P and P, you cannot have this as an answer. You cannot have 5 into 4 into 3 into 1 as an answer, because you need to consider the fact that P is actually repeating twice. In other words, it doesn't matter if this is the P, if let's say A P P L E, it doesn't matter if the slot 5 is filled in with the P of this one or this one. It doesn't matter if you fill in the third slot with this P or this P. It's the same thing, and that's why you have to consider that P is being repeated. So what I'm trying to say is that, let's say if I assume that this was a general case of permutation, and I just calculate the total permutations for these alphabets, and let's say I list all of them, so I would get, let's say, P L P and A P L E P and A P E L P. Let's say that there would be two copies of the same thing. So in the all the permutations that are possible of these five alphabets, for every single listing that you can get to, there would actually be two copies of the same thing. So there would be two AEPLP in the total number of permutations for these five alphabets. Why is that there will be two copies of the same thing? Because in the first one we fill in the third slot with this P, and in the second copy we fill in the third slot with this P. So there will be two copies of every single word that is formed using these five alphabets, because there are two P's in this number. So in order to solve this problem that we have, we actually divide the total permutation that we have gotten by the total number of repetitions or copies there are. So because I said that there are two copies for every single word that you can write in these list of permutations, I would actually divide this number with 2. How do I know that there would only be two copies of every single word that can be formed in these permutations? Is that I can just check it by applying the permutation for the two for the two by applying the permutation for the two alphabets that there are. So for example, for the two alphabets, which is P and P, they fill in two slots in every single word. So let's say in the first slot there are two choices that I can fill it with, which is P and P. And after I have filled the first slot with one of these P's, the leftover P will be filled in the second slot, and that gives me 1. So there are actually two possible permutations in which these two P's can be rearranged, and that's how I know, and that's why I can divide these total permutation value with 2 to get my answer as 5 into 4 into 3 into 2 into 1 by 2, which gives me 60 as the total value, number of words that can be formed using these five alphabets as choices. And that was the case of permutation with repetition that had limited repetition allowed. In general case of permutation, we generally have unique and distinct samples as choices. Let's say 1, 2, 3, 4, or S, H, Y, R as the number of choices that you can fill in the slots. Let's say there are 3 slots to fill in with these 2 choices. But the thing is, there would be no repetition allowed in the general case of permutation, because all of these elements that we have in these 2 samples are actually very distinct from each other. So once any of these values have been filled in the first slot, then the same value would not be available for the second and the third slot. So for the general case of permutation, we just look at the available choices for the first one, which is 4 choices here as well as here. So we have 4 choices for the first slot, and then because one choice has already been filled in the first slot and it's not available for the second slot, we will have 3 choices for the second slot and 2 choices for the third slot, and we multiply these numbers to get the total permutation that are possible using 4 elements that are available as a choice. And these permutation would be these permutation would include numbers like 1, 2, 3, 3, 2, 1, 3, 1, 2. But one thing you can observe in these selected choices, in the first case there is 1, 2, 3, and in the second case the same numbers are rearranged in different order. So 1 has been transferred to the third slot and the 3 is transferred to the first slot, and that would give me 321. So these are the sort of things that are allowed in general cases of permutation. But this is actually not allowed in combination, which we'll talk about later. But in order to find out the value in just general case of permutation, you just multiply the number of choices that you have, which are 4 for the first, 3 for the second, and 2 for the third, which would give you 24 as the answer. But before we move on to combinations, let's take a small examples in order to understand this even better. Let's say we have 2 available slots and we have to fill it in with 2 numbers, which is only 0 and 1. So there are 2 choices and 2 available slots to be filled with these 2 choices. If I had to calculate this using the method that I have been using so far, if I had to calculate the permutations possible for these 2 slots using these 2 choices, I would know that I have 2 choices in this first slot and only 1 choice for the second slot, because 1 has already been taken for the first slot. So I have 2 possible permutations, and those 2 possible permutations would be, if I had 0 and 1 as choices, would be 0, 1 and 1, 0. These are the only 2 values of permutations that is possible using these 2 choices and filling in with 2 slots. So if I had to do the same thing with the case of bland repetition, if it was a case of bland repetition in permutation where repetition is allowed blandly, you would just know that you can fill the first slot with 2 choices and as well as the second choice with 2 choices, because repetition doesn't matter. So I would get the numbers that I would get would be 4. The total numbers that I can form would be 4. Total permutation that I can find would be 4, and the numbers would be 0, 1, 0, 0, 1, 1, and 1, 0. These would be the 4 cases of permutations that would be possible if repetitions were allowed. For example, 0, 0 and 1, 1 was allowed. Therefore, I had 4 available permutation cases in a case of bland repetition. Now let's head on to the difference between combination and permutation is that rearrangements are not allowed. And what it means is that if, say, I had the same thing again, if I had 1, 2 and 3 as the available choices and I had to fill 2 slots with it and I had to find permutations, then I would get 3 for this and 2 for this. That would make it 6 possible permutations. 1 2, 1 3, 2 1, 2 3, 3 1, and 3 2. Observe that in all of these numbers none are repeated, but also observe that some of the numbers are rearranged. For example, 1 3 is the same thing written backwards, and 2 1 is the same thing written forwards. So I have two rearrangements of 2 and 1, two rearrangements of 3 and 1, and two rearrangements of 2 and 3, which is 2 3 and 3 2. So this is actually not allowed in combination. If it was a calculation combination, only one of these rearrangements would be allowed and other one would be discarded. So this would be discarded because this is a rearrangement of this, and this would be discarded because this is a rearrangement of this, and this would be discarded because this is a rearrangement of this. So I would have been left with only 1 2, 1 3, and 2 3 as the possible answer, which would make it 3 possible combinations. So that's what I mean when I say rearrangements are not allowed. You cannot rearrange the same numbers from first slot to the second slot. So in order to find the combinations, what we generally do it, we find permutation for the available choices. So let's say I had to fill 3 slots and I had 5 choices. Permutation that I would find is that the first slot would be filled with 5 of these choices, and the second would be filled with 4 of them, and the third would be filled with 3 of them. So the permutation would be 5 into 4 into 3, which equals 60. 60 would be the case of permutations. But because, like I said, rearrangements are not allowed, how do we find the number of rearrangements that are possible, that we have to eliminate from these total permutations? Rearrangements are possible once all of the values have been selected, already predetermined. That's when we calculate how many rearrangements are possible. So for example, if I have to find rearrangements, I'm going to assume that 5 has been selected for the first slot, and let's say 3 has been selected for the second slot, and let's say 1 has been selected for the third slot. So how many ways in which 531, 531 can be rearranged? That's what I have to find the number of to eliminate the number of rearrangements. So 531 can be rearranged in the same way that we calculate the value of permutations. So we have 5, 3 and 1 as the sample, and we have to fill in these 3 slots. So the first slot can be filled in with all of these 3 numbers, which is 3. Any of these 3 numbers can be filled in the first slot, and in the second slot you can fill it in with 1 less than the first slot because 1 is already taken in the first, and for the last one we have only 1, which gives me 6 as the total value of rearrangements. So there are 6 possible ways in which 531 can be rearranged, and they are 531, 513, 153, 135, 351, and 315. These are the 6 possible rearrangements that are possible using 135 as samples, as choices. So out of all these 6 numbers, only one is viable and the rest will be discarded. And therefore I divide the total number of permutations that has been found, which includes all of these rearrangements, by the total number of rearrangements that are possible, which is 6, and that would give me 10 as the total combination values. And 10 values of combinations there are in which there are no rearrangements. This is what you call combination, where every number is unique.